Water splitting is the general term for a chemical reaction in which water is separated into oxygen and hydrogen. Efficient and economical water splitting would be a key technological component of a hydrogen economy. Various techniques for water splitting have been issued in water splitting patents in the United States. In photosynthesis, water splitting donates electrons to the electron transport chain in photosystem 2. Electrolysis. Electrolysis of water is the decomposition of water into oxygen and hydrogen gas due to an electric current being passed through the water. In chemistry and manufacturing, electrolysis is a method of separating chemically bonded elements and compounds by passing an electric current through them. One use of electrolysis of water or artificial photosynthesis is to produce hydrogen. Recently, researchers have shown that water splitting can be broken into two discrete steps using polyoxymetallate-based redox mediators. Power-to-gas production schemes. The excess power or off-peak power created by wind generators or solar arrays is used for load balancing of the energy grid by storing and later injecting the hydrogen into the natural gas grid. Production of hydrogen from water requires large amounts of energy and is uncompetitive with its production from coal and natural gas. Potential electrical energy supplies include hydropower, wind turbines, or photovoltaic cells. Usually, the electricity consumed is more valuable than the hydrogen produced, so this method has not been widely used. Other potential energy supplies include heat from nuclear reactors and light from the sun. Hydrogen can also be used to store renewable generated electricity when it is not needed and then used to meet power needs during the day or two. Fuel vehicles. The storable quality of hydrogen helps make hydrogen an enabler of the wider use of renewables and internal combustion engines. High-pressure electrolysis. When water is pressurized and then electrolysis is conducted at those high pressures, the produced hydrogen gas is pre-compressed at around 120 to 200 bars. By pre-pressurizing the hydrogen in the electrolyzer, energy is saved as the need for an external hydrogen compressor is eliminated. The average energy consumption for internal compression is around 3%. The energy required to compress water is very much less than that required to compress hydrogen gas. High-temperature electrolysis. When the energy supplied is in the form of heat, the best path to the production of hydrogen is through high-temperature electrolysis. In contrast with low-temperature electrolysis, HTE of water converts more of the initial heat energy into chemical energy, potentially doubling efficiency to about 50%. Because some of the energy in HTE is supplied in the form of heat, less of the energy must be converted twice, and so the process is more efficient. HTE processes are generally only considered in combination with a nuclear heat source, because the other non-chemical form of high-temperature heat is not consistent enough to bring down the capital costs of the HTE equipment. Research into HTE and high-temperature nuclear reactors may eventually lead to a hydrogen supply that is cost-competitive with natural gas steam. Reforming HTE has been demonstrated in a laboratory, but not at commercial scale. Photoelectrochemical water splitting, using electricity produced by photovoltaic systems, potentially offers the cleanest way to produce hydrogen. Again, water is broken down into hydrogen and oxygen by electrolysis, but the electrical energy is obtained by a photoelectrochemical cell process. The system is also named artificial photosynthesis. Photocatalytic water splitting. The conversion of solar energy to hydrogen by means of water splitting process is one of the most interesting ways to achieve clean and renewable energy. However, if this process is assisted by photocatalysts suspended directly in water rather than a photovoltaic or an electrolytic system, The reaction takes place in one step, it therefore can be more efficient. Radiolysis. Nuclear radiation routinely breaks water bonds. In the Mponeng gold mine, South Africa, researchers found in a naturally high radiation zone, a community dominated by a new phylotype of D-sulfotomaculum, feeding on primarily radiolytically produced H2. Spent nuclear fuel, nuclear waste, is also being looked at as a potential source of hydrogen. Photobiological water splitting. Biological hydrogen can be produced in an algae bioreactor. In the late 1990s it was discovered that if the algae are deprived of sulfur it will switch from the production of oxygen, i.e. normal photosynthesis, to the production of hydrogen. It seems that the production is now economically feasible by surpassing the 7 to 10% energy efficiency barrier, with a hydrogen production rate of 10 to 12 milliliters per liter culture per hour. Thermal decomposition of water. Thermal decomposition, also called thermolysis, is defined as a chemical reaction whereby a chemical substance breaks up into at least two chemical substances when heated. At elevated temperatures, water molecules split into their atomic components hydrogen and oxygen. For example, at 2200 degrees Celsius about 3% of all H2O molecules are associated into various combinations of hydrogen and oxygen atoms, mostly H2O, O2, and O. Other reaction products like H2O2 or HO2 remain minor. At the very high temperature of 3000 degrees Celsius, more than half of the water molecules are decomposed. But at ambient temperatures, only one molecule in 100 trillion dissociates by the effect of heat. Thermal water splitting has been investigated for hydrogen production since the 1960s. The high temperatures needed to obtain substantial amounts of hydrogen impose severe requirements on the materials used in any thermal water splitting device. For industrial or commercial application, the material constraints have limited the success of applications for hydrogen production from direct thermal water splitting, and with few exceptions, most recent developments are in the area of the catalysis and thermochemical cycles. Nuclear thermals and prototype generation IV reactors, such as the HTTR, operate at 850 to 1000 degrees Celsius, considerably hotter than existing commercial nuclear power plants. General Atomics predicts that hydrogen produced in a high-temperature gas-cooled reactor would cost $1.53 per kilogram. In 2003, steam reforming of natural gas yielded hydrogen at $1.40 per kilogram. At 2005 gas prices, hydrogen cost $2.70 per kilogram. Hence, just within the United States, a savings of tens of billions of dollars per year is possible with a nuclear-powered supply. Much of the savings would translate into reduced oil and natural gas imports. One side benefit of a nuclear reactor that produces both electricity and hydrogen is that it can shift production between the two. For instance, the plant might produce electricity during the day and hydrogen at night, matching its electrical generation profile to the daily variation in demand. If the hydrogen can be produced economically, this scheme would compete favorably with existing grid energy storage schemes. What is more, there is sufficient hydrogen demand in the United States that all daily peak generation could be handled by such plants. Recent research on the hybrid thermoelectric copper-chlorine cycle has focused on a cogeneration system using the waste heat from nuclear reactors, specifically the CANDU supercritical water reactor. solar thermal. The high temperatures necessary to split water can be achieved through the use of concentrating solar power. Hydrosol-2 is a 100 kilowatt pilot plant at the Plataforma Solar de Almería in Spain, which uses sunlight to obtain the required 800 to 1200 degrees Celsius to split water. Hydrosol-2 has been in operation since 2008. The design of this 100 kilowatt pilot plant is based on a modular concept. As a result, it may be possible that this technology could be readily scaled up to megawatt range by multiplying the available reactor units and by connecting the plant to heliostat fields of a suitable size. An interesting approach to solar thermal hydrogen production is proposed by H2 power systems. Material constraints due to the required high temperatures above 2200 degrees Celsius are reduced by the design of a membrane reactor with simultaneous extraction of hydrogen and oxygen that exploits a defined thermal gradient and the fast diffusion of hydrogen, with concentrated sunlight as heat source and only water in the reaction chamber. The produced gases are very clean, with the only possible contaminant being water. A solar water cracker with a concentrator of about 100 square meters can produce almost 1 kilogram of hydrogen per sunshine hour. Water splitting by coordination compounds huge energy requirements. The expected shortage of petroleum in the future and quick rise in pollution of the problems that need to be addressed by putting more efforts into investigating clean and sustainable energy resources. In pursuit of such energy sources, efforts are being put in light-driven splitting of water into O2 and H2 in an attempt to convert solar energy into fuel. Water oxidation is the first important step, providing the necessary electrons and protons for the next step, in which hydrogen production takes place in a catalysis reaction by a proton reduction catalyst to H2O plus HV to H2 plus O2 increment G degree equals 4.92 electron volts for H plus plus 4E to H2 to H2O for H plus plus 4E plus O2. The water oxidation step has been considered the bottleneck of this process, so the designing of highly active and robust water oxidation catalysts is an important step in the development of light-driven water splitting. Water oxidation catalysts minimize the overpotential and increase the reaction rate. An ideal WOC is required to possess low overpotential, high stability, high activity, efficiency, low toxicity and low cost. General steps in water oxidation catalysis. First step in the water oxidation catalysis by WOCs is the transfer of electron from the catalyst to the oxidizing agent, which can be enhanced by introducing strong electron-donating ligands in the catalyst. Second step involves the water oxidation, for which the redox potential of the catalyst should have a high oxidizing power at the highest oxidation state. The third step, which is the OO bond formation, has been investigated to proceed by two mechanisms. Water nucleophilic attack, in which water attacks the oxo group of the metal complex, resulting in 2-electron reduction of the metal and O2 formation, and interaction of two MO species, which leads to the formation of peroxo intermediate. The last step is the release of the molecular oxygen, which is a slow step. Water splitting in photosynthesis. In nature, the solar energy is converted to chemical energy by the process of photosynthesis, producing energy essential for the survival of life on Earth. Photosynthesis works with two photosystems, photosystem I and photosystem II. When photosystem I gets photoexcited, electron transfer reactions gets initiated, which results in reduction of a series of electron acceptors, eventually reducing producing NADP plus 2 NADPH and PSI is oxidized. The oxidized photosystem I captures electrons from photosystem 2 through a series of steps involving agents like plastoquinone, cytochromes and plastocyanine. The photosystem 2 then brings about water oxidation resulting in evolution of oxygen, the reaction being catalyzed by CAMN405 clusters embedded in complex protein environment. The complex is known as oxygen-evolving complex. Water splitting by some metal complexes. Water splitting by coordination complexes got its inspiration from the natural photosynthesis. These coordination complexes are used as catalysts in water splitting or water oxidation and hence being called water oxidation catalysts. There are a number of synthetic metal complexes used for this purpose. A brief review is given below. Water splitting by ruthenium complexes. Among a number of WOCs known to us, ruthenium-based complexes are known to exhibit high turnover numbers in catalytic activity. A number of mononuclear Ru catalysts have been reported to be efficient catalysts, which have caused us to believe that multi-centered catalysts are not necessarily for robust catalytic activity. Tanaka, Mayer, Lobert, and the co-workers have reported the synthesis of some ruthenium aquacomplexes which are active in water oxidation, and the catalytic mechanisms have been studied extensively mainly based on the 6-coordinate ruthenium models. Lobert and co-workers investigated 3+pyrazolate. A number of non-aqua complexes 2,2+ where pyridine 2, 6-DIYL, bis Py equals pyridine, R equals CH3, CF3 and N2 have been reported by Thummel al. and shown to be highly active in the process. Duan al. synthesized a mononuclear complex 1 and isolated a rare 7-coordinated RUIV dimeric intermediate 2,23,2 hydrogen oxide during its water oxidation catalytic reaction. The intermediate was found to have a bridging ligand in addition to 2 water molecules, which appears in the form of H bonding with the intermediate. Strong electron donating ability of carboxylate groups in the complex causes more lowering of the oxidation potential of the complex 1 as compared with the complex 2+-1, 10-phenanthroline, reported by Thummel al. Chemical investigation of the catalytic process involved a huge liberation of oxygen when the complex was added to an aqueous trifolic acid solution, with a CEIV oxidant. Duan al. also reported the synthesis of another mononuclear ruthenium complex which has improved catalytic activity towards water oxidation as compared with another structurally similar mononuclear complex 1. Highly polarizable by a system of isoquinones on the axial positions in 3 reduces the barrier for radical dimerization of Ru-O because of non-covalent attractive interactions between them as compared with the 4 picolines in complex 2, which make it a better catalyst. The catalytic activity is comparable to that of the photosynthetic photosystem 2, the driving force being CEIV instead of visible light for the complex. Water splitting by nickel complexes. Nickel-based homogeneous catalysts are hard to find in the literature, but they have been used as alkaline electrolyzers on the commercial scale. A Ni-based oxide film has been synthesized which liberates oxygen in quasi-neutral conditions at an overpotential of 425 mV and shows long-lasting stability. The X-ray spectroscopy revealed the presence of dimicrooxide bridging between Ni and NiIV ions, but no evidence of monomicrooxide bridging was found between the ions. Similar structures can be found in co-WOC films and MN-WOC catalysts. Water splitting by cobalt complexes. Cobalt salts can be used as WOCs, but the water oxidation capability decreases with the passage of time because of the precipitation of the salt from the homogeneous solutions, resulting in turbidity. Kainan and Nacera have demonstrated the formation of a dark thin film over the surface of indium tin oxide which was used in electrode, along with bubbling in the solution. These bubbles were confirmed to be of oxygen. Co-WOCs have been shown to work very efficiently at a pH 7.0. Heterogeneous cobalt oxide have been investigated to work on the same pattern as other cobalt salts. No mechanism has been reported so far for these WOCs. A homogeneous cobalt polyoxametallate complex 10 have been described to be highly efficient as compared to the reported heterogeneous cobalt complexes, reported by Yin et al. Zidke et al. Prepared stable WOCs by adsorbing Co-E as Co2 clusters on silicon nanoparticles which exhibited a high water oxidation activity. A homogeneous WOC2 was reported by Walenko and co-workers. The complex undergoes a proton-coupled electron transfer to form a stable 2+ species which on further oxidation forms a coev intermediate. The intermediate formed reacts with water to liberate O2. Water splitting by ion complexes. Julio and co-workers demonstrated that common ion complexes catalyze water oxidation reactions to produce O2. A water-soluble complex was reported to be a very efficient catalyst for water oxidation when an oxidant was added and hence liberated oxygen bubbles. The concentration of the catalyst and the oxidant were found to be strongly affecting the oxidation process. Catalytic activity of the complexes and cyclohexane 1,2-diamine BP equals N bis 2 bipyrrolidine MEP equals N dimethyl N bis ethane 1,2-diamine TPA equals trisamine were studied, which showed them to be active catalysts. All these complexes have two accessible sites for coordination CIS to each other. The complexes were found to undergo degradation in a few hours of activity because of strong acidic and oxidizing environment. Another complex 2 was found to show low catalytic activity, and 2 were found to be inactive. Both possess 2 trans and only 1 coordination site, so it could be referred that the presence of CIS reactive sites is a key factor for water oxidation catalysis in the aforementioned complexes. Water splitting by iridium complexes. Iridium oxide is a stable bulk catalyst with low overpotential. McDaniel et al. Synthesized analogues of plus with high turnover numbers, but low catalytic rates. Replacing PPY of the complex with CP** resulted in an increase in the catalytic activity but decreased the turnover number. Water nucleophilic attack on IR equals O species was found to be responsible for the O2 formation, so it could be concluded that a number of complexes of iron, ruthenium, cobalt, iridium and many others can be used for water oxidation in artificial photosynthesis. The use of these complexes is reliable in terms of high energy production and is more environment friendly than the commonly used fuel. Several of these WOCs have good tons and TOFs, but unfortunately none have reached to the point of using on large scale as they lose their activity after some time due to multiple reasons or because they are slow to react. Intense research is required in the field to design the ideal WOCs that can be used on the commercial scale. Chemical production. A variety of materials react with water or acids to release hydrogen. Such methods are non-sustainable. In terms of stoichiometry, these methods resemble the steam reforming process. The great difference between such chemical methods and steam reforming is that the necessary reduced metals do not exist naturally and require considerable energy for the production. For example, in the laboratory, strong acids react with zinc metal in Kip's apparatus. In the presence of sodium hydroxide, aluminium and its alloys react with water to generate hydrogen gas. Unfortunately, due to its energetic inefficiency, aluminium is expensive and usable only for low-volume hydrogen generation. Also, high amounts of waste heats must be disposed. Although other metals can perform the same reaction, aluminium is among the most promising materials for future development because it is safer, cheaper and easier to transport than some other hydrogen storage materials like sodium borohydride. The initial reaction consumes sodium hydroxide and produces both hydrogen gas and an aluminate byproduct. Upon reaching its saturation limit, the aluminate compound decomposes into sodium hydroxide and a crystalline precipitate of aluminum hydroxide. This process is similar to the reactions inside an aluminium battery. Null for sodium hydroxide plus Al3 overall, Al plus 3H2O Al3 plus 1.5H2. In this process, aluminium functions as a compact hydrogen storage material because 1 kilogram of aluminum can produce up to 0.111 kilograms of hydrogen from water. When employed in a fuel cell, that hydrogen can also produce electricity, recovering half of the water previously consumed. The U.S. Department of Energy has outlined its goals for a compact hydrogen storage device, and researchers are trying many approaches, such as by using a combination of aluminum and NaBH4 to achieve these goals. Since the oxidation of aluminum is exothermic, these reactions can operate under mild temperatures and pressures, providing a stable and compact source of hydrogen. This chemical reduction process is specially suitable for backup remote marine applications. While the passivation of aluminum would normally slow this reaction considerably, its negative effects can be minimized by changing several experimental parameters such as temperature, alkali concentration, physical form of the aluminum, and solution composition. Patents. Vienna, U.S. Patent 28793, improved method of using atmospheric electricity, June 1860.